Hello again. So in the last lecture, we looked at solutions of Schrodinger's equation. In other words, we looked at the wave functions of electrons in atoms. Or in other words, we looked at the shapes of atomic orbitals and their relative energies. We ended up thinking about two rules that will help us determine how electrons can be distributed amongst atomic orbitals in order to achieve the lowest energy configuration. We call the lowest energy configuration the ground state. Now, since the energies of individual orbits are such a big contributor to any total energy, it makes sense that putting electrons in the energetically lowest possible orbital will give us the lowest energy configuration. Of course, you could put an electron in any orbit, but if it's not the lowest one, then this will be an excited state electronic configuration for your atom. Now with hydrogen, we have just one electron in orbit around a nucleus. So the energy of the orbitals depends only upon the value of the principal quantum number, n. So the 1s orbital, where n equals 1, is lowest, and the 2s orbital and all three of the 2p orbitals all have the same energy, because they have the same value of n. We say any orbital that has the same energy are degenerate. In this case, the ground state is obtained when we put the one electron into the 1s orbital. The shape of the hydrogen atom is thus the shape of the 1s orbital with one electron in it. Now when we move along to the next element, that's helium, remember helium has one nucleus and two electrons. The addition of an extra electron really starts to complicate the picture. There is now a new type of interaction. As well as the attraction between each electron and the nucleus, there is also now repulsive electrostatic interaction between the two electrons. This interaction removes the degeneracy between the orbitals in different subshells. What I mean is that in helium and all heavier elements, the 2s and the 2p orbitals are now no longer degenerate. They have slightly different energies. In fact, the 2p orbitals are raised a little bit relative to the 2s. This comes about because the different shapes of the orbitals. The electron-electron interactions, or repulsion, is not the same between an electron in the 1s orbital and the electron in the 2s orbital compared to an electron in the 1s orbital and its interaction with an electron in a 2p orbital. Clearly, the energy of orbitals is dependent upon the number of electrons present in the atom, and this becomes more and more important as we add in more and more electrons. It's easy to see why this might be the case, just by thinking about the sheer number of pairwise electron-electron interactions. While helium, with its two electrons, has just one electron-electron interaction to worry about, what about an atom like calcium? The neutral atom of calcium has 20 electrons. That's 190 different pairwise electron-electron interactions in a calcium atom, which will all contribute to the total energy of a particular electronic configuration. These interactions mean that the energies of different orbitals are different for different numbers of electrons and for different elements. In some cases, this even results in a different ordering sequence of the atomic orbitals. No need to panic, we'll get to that later. For the electronic configuration of helium, with its two electrons, we can still focus on the lowest lying orbital. Remember that the Pauli exclusion principle says that no two electrons can be described by the same set of quantum values. But the fact that the ms quantum number can take one of two possible values means that we can get up to two electrons in each orbital. So the ground state for helium is to have both electrons in the 1s orbital with opposite values of spin. Now, there are several different ways of representing electronic configurations. One method you may have encountered before is this system of boxes and arrows, and we will use it for the moment here. Each box represents an orbital, and each arrow represents an electron. Arrows can be pointing up or down to represent the different MS states. And so the simple rule is you can't have two parallel arrows in the same box. When I say parallel, I mean two arrows pointing in the same direction. We use the term anti-parallel to describe arrows pointing in opposite directions. So here is how we represent the configurations of hydrogen and helium. The next element is lithium with 3 electrons. There is no room in the 1s orbital for a third electron. So we need to place it in the next available space. It can go in the 2s orbital. Moving to the element number 4, that's beryllium, we need to add in one more electron. It can also go into the 2s orbital as long as we make sure that it has the opposite spin to the electron that was already present in the 2s orbital. Now both the 1s and the 2s orbitals are full, and the next element is boron. Now the 5th electron has to go into one of the 2p orbitals, and this gives us the correct ground state for boron. So far, so good. But the next element is carbon, and there's an ambiguity here. Where should we put the 6th electron? Should it be parallel or anti-parallel? Should it be in the same box or another box? We need to refer to Frederick Hund for this answer. Hund gives us a third rule, which we can apply to any situation where we have degenerate orbitals, i.e. more than one orbital with the same energy. Hund's rule says you will obtain the ground state, the lowest energy configuration, if, when given the choice, you put electrons in different orbitals with their spins all aligned in the same direction, i.e. spins parallel. That's clear, but why? There are 2 points to this, but both come down to the same thing. It's energetically costly to put 2 electrons close to each other because of the electrostatic repulsions between them. Reduce the repulsions and you'll get a lower energy solution. So in this case, since our different degenerate orbitals occupy a different physical space, then it is clearly advantageous to put different electrons into different orbitals. 2 electrons in the same orbital are clearly as close as they can get. So given the choice, let's not do that. The second point concerns the alignment of spins. The motion of electrons in atoms is highly correlated. The electron-electron repulsions mean that they're constantly trying to get away from each other. It turns out that electrons with the same spin, all up for example, do a much better job of avoiding each other than as do 2 electrons of opposite spins. So spins parallel is the lower energy solution. Okay, let's get back to the electronic configurations. We can now apply Hund's rule to carbon, and we have 2 electrons in 2 separate p orbitals with the same spin. Nitrogen has 1 more electron. This has to go in the 3rd p orbital, again with the same spin orientation. Oxygen has 1 more electron, but there's no choice here. We must put it in one of the half-filled p orbitals, and it must have an opposite sign for the spin. It's the same story with fluorine, and again with neon. With all of its 10 electrons, we have completely filled the 1s, the 2s, and all 3 of the 2p orbitals. While these boxes and arrows are a useful way to think about electronic configurations, they are not always easy to write or inherently explicit enough. So there are other ways to represent electronic configurations. We can write out the symbol for the wave function and add a superscripted number after the symbol to indicate how many electrons are in that orbital. So the electronic configuration for hydrogen could be written as psi 1s superscript 1. For helium, it would be psi 1s superscript 2. And for lithium, where we need to use 2 orbitals, we just write this down as a sequence. So the configuration for lithium becomes psi 1s superscript 2, psi 2s superscript 1. This is easily written, and much more explicit as to where the electrons are. So from now on, we won't use boxes and arrows when we write out configurations. Now, when we have lots of electrons and lots of orbits, and every electron is in some sort of orbital, we usually forget about writing the size symbol for an orbital. We just write the number value and the letter value for the n and the l quantum numbers as a label for an atomic orbital. So we can simplify our nomenclature by just writing 1s1, meaning 1 electron in a 1s orbital, or 1s2 for helium, meaning 2 electrons in a 1s orbital. So we can scrap the use of the symbol phi. In this system also we do not need to specify if the spin is up or down. That is because we don't know if it's up or down. We know it's one or the other, and the rules tell us when the spins are paired, antiparallel, or not. We also do not specify which p orbital is occupied. How could we? We don't know which one is. We just know that how many are. So when we write 2p, we mean the collection of the 3 different 2p orbitals that can clearly accommodate up to, but no more than, 6 electrons. The rules tell us how the electrons are distributed in this group of orbitals. We can carry on this process from sodium all the way through to argon. Simply following these rules gets us the correct electronic configuration for all of these elements. The key thing here is to know the energy sequence. It starts with n equals 1 and the 1s orbital, and then we have n equals 2. The electron-electron interactions means that the 2s orbital is lower in energy than the 2p, so we fill those first. Next is n equals 3. Those electron-electron interactions remove some of the degeneracy, and the 3s is the lowest, and then the 3p, and then the 3d. So beyond argon is our first little anomaly. In argon, we have filled 3 different 3p orbitals. We know that there are 5 3d orbitals that are a little higher in energy than the 3p orbitals. However, that is not where the next electron goes. So the next element is number 19, that's potassium. And the 19th electron actually goes into a 4s orbital. What that means very simply is that the 4s orbital is in fact lower in energy than the collection of 5 3d orbitals. So that is why we populate it first. However, these 2 types of orbitals, the 4s and the 3d, are very close in energy, and under some circumstances the order is reversed, and 3d is effectively lower than 4s. And so for the calcium atom, there are 2 electrons in the 4s orbital, and then the next element is scandium, and that is the first element in the transition metal series, and this has 1 electron in 1 of the 5 distinct 3d orbitals. So this handy graphic may help you remember the filling order of orbitals. Though it's not universal for all elements at all times, it mostly gives us the right answers. There are still a couple more things to say about electronic configurations. We can keep going with these rules, and we usually get the right configurations. I want to be clear that in different textbooks you might see some discrepancies in the order of the orbitals, such as here for scandium. Sometimes it's written as 3p6, 3d1, 4s2, but in other books you might see it written as 3p6, 4s2, 3d1. It really doesn't matter. These are the same configurations. As I've said, the 3d and the 4s orbitals are actually very close in energy. By the time we get to element 36, though, we're at krypton, and you can see there is a long and detailed electronic configurations that are becoming rather cumbersome. And it's only going to get worse. For example, gold has 79 electrons to account for. Oganesson has 118. There is a way to simplify it. But before we get to that, I want to pick up on one family, one group of elements, and look at their configurations. Let's have a look at group 18, the noble gases. These are famously unreactive. What that means is they must have particularly stable electronic configurations if there is no need to or desire to change them. Here are those configurations. What you will notice, the thing that they all have in common, is that every shell and every subshell is full. There is no space in the low-lying orbitals. The s orbitals all have 2 electrons in them. The p orbitals are a group of 3 p orbitals and so can accommodate 6 electrons. And the set of 5d orbitals all have a maximum of 10 electrons in them. This is a very common feature of elements. Whenever we find orbitals to be full, we always have an additional stability. The other feature I want to point out using these electronic configurations is that not all orbitals contribute to the character of an atom equally. When an atom interacts or bonds with other atoms, it is the outermost part that is doing the interacting. It is the electrons in the outermost orbitals that will be most perturbed by any bonding interaction. Now, it is the principal quantum number, at large n, that largely determines the size of an orbital. And for any particular electronic configuration, the highest values of n are at the end of that configuration. These are the electrons that are least well held by the atom, since these are the electrons that are on average furthest from the nucleus. So we can make a distinction between inner electrons, with relatively small values of n, and the outermost electrons, which shape the outside of the atom and have the largest values of n for that particular configuration. Look, I've coloured the outer electron orbits in blue. We can call the inner electrons the core electrons, and you'll notice that the sets of core electrons actually correspond to the configurations of the preceding noble gas. The core electrons for neon are really the helium configuration. The core electrons for argon are the neon configuration. By contrast, the outermost electrons are referred to as the valence electrons. These are the important ones. So let's have a look at our list of configurations from hydrogen to argon again. We can identify the stable configurations associated with the group 18 elements. These are highlighted in pink. After each noble gas element, we begin to fill a new, larger shell. This leaves the stable noble gas configurations as a set of core electrons, shown here in blue. And then this leaves behind the most important outer or valence electrons. It's these electrons, the valence electrons, that determine the characteristic chemistry of an element. A better way to write out the electronic configuration, because it separates out the core and the valence electrons, is to write the electronic configuration as a noble gas in square brackets, meaning these are the core electrons, and then just to list the valence electrons in detail. This makes the situation much less confusing when we have many electrons and allows us to focus on where the most important electrons are. Using this shorter form of the electronic configuration, let's compare some atoms from particular groups. Let's start with the first group in the periodic table, group 1, the alkali metals. If we look at the outermost shell of each of these atoms, there is one electron in an s orbital. All of these orbitals have the same basic shape, especially on the outside. The only real difference is as we descend the group, the principal quantum number increases, and so too does the size of the orbital. No surprise that with such strikingly similar outer electronic configurations, they all show such similar chemistry. Let's have another look at another group. Let's take group 13 from boron through to thallium. If we look at the valence electrons, they're not all exactly the same. Gallium and indium and thallium also have 10 electrons in a set of d orbitals. And thallium also has 14 electrons in a set of f orbitals. But the last orbital to have an electron added is a p orbital, and there all the configurations end up with a something p1. Note also that the s and the p orbitals also share the same value of principal quantum number, and for each element, s and the p orbitals have the highest value, and so these orbitals are more extensive and more on the outside than any other so-called valence electrons. So in gallium, 10 of the electrons are in d orbitals, but these are smaller and more compact compared to the 4s and the 4p orbitals. This combination of being filled and being smaller means that these orbitals are not so important in the chemistry of this element. It is the filled s orbital and the incomplete p orbital that are more important, and this is the same for the whole of this group. It's really useful to understand how the filling of orbitals or groups of orbitals maps back onto the periodic table. We can code each element on the table with the last orbital being filled by an electron. Color coding these values by the principal quantum number really helps us to see how the observed structure of the periodic table is related to the relative energies of the different orbitals. So it's not exactly true that each row corresponds to a particular value of n. It is true for the main group, but the values for the principal quantum numbers in the d block and the f block are staggered. Of course, we can also color code on the value of the angular momentum quantum number L. This maps the blocks of the periodic table. Two unusual features here being that 1. Helium is clearly an s block element, although we align its chemistry better with the elements of group 18 in the p block. And 2. Notice that the f block seems to split the d block. Well, the 5d and the 6d orbitals. What's going on here is at that point of the periodic table, the 6s, the 5d and the 4f sets of orbitals are all very similar in terms of energy. And again, the 7s, the 6d and the 5f orbitals are also very similar in terms of energy. By thinking about the structure of the periodic table in this way, we can realize a much simpler way of determining the electronic configuration of an element. We can, in fact, read it directly from the table, and here's how. Suppose you want to find the electronic configuration of an element. Suppose we choose vanadium. First of all, we have to find vanadium on the periodic table. And then we need to count backwards through the spaces of the preceding elements until we get back to the next preceding noble gas. And that's your configuration. So vanadium is 3 squares in to the first row of the D block. So the last part of the configuration will be 3D superscript 3. And then there are 2 squares in the S block corresponding to the filling of the 4s orbitals before that. So there's a 4s superscript 2 part to the configuration. And then the previous element is argon. So that's our noble gas, and that's the configuration of the core electrons in vanadium. Reading forwards now, for the electronic configuration of vanadium, it is an argon core with a 4s2, 3d3 configuration. No need to assign all 23 electrons in this element. So the last thing I want to say at the moment is I want to highlight a couple of apparent anomalies in the configurations. As we fill the 3d orbitals for the first row of the transition metals, we might have expected copper to show a 3d9 4s2 configuration, but it actually shows a 3d10 4s1 configuration. Similarly, we might have expected chromium to show a 3d4 4s2 configuration. It's actually 3d5 4s1. What this means is simply that the observed configuration is lower in energy than the configuration we might have expected. We already know that the energy associated with the 4s and the 3d orbitals is very similar, and we also know that closed shells or subshell configurations, by which I mean any filled set of orbitals, are often associated with a greater stability. This is most evident at the end of the p block in group 18, but it is also true to some extent for the end of each of the other blocks. Clearly, having 10 electrons in a 3D orbital trumps having 9. This also happens to be true for half-filled subshells. So the 3D5 configuration, where there is 1 electron in each of the 5 different d orbitals, carries a little bit of extra stability, and this is the configuration we see. Okay, that covers a lot of detail about how we assign electronic configurations in an atom, and that's all I want to say on this topic for the moment. Thanks for watching.